Now that we've learned a little bit more about equilibrium, it's time to focus on a little bit of the special case equilibrium. And the first stopping off point is going to be to talk about acids and base equilibria. Before we can get into too much of the nitty-gritty, I think it might be a good idea to remind ourselves a little bit more about acids and bases and also electrolytes. So first, I just want to focus in on strong electrolytes. Strong electrolytes are any compound that, when it's dissolved in water, will dissociate to 100%. Now that actually includes a very narrow list of compounds. They can be your 7 strong acids, which you should remember what those are, but I'll remind you in just a moment. Your strong bases, which will include any hydroxide with an cation ion from either group 1 or limited from group 2, and essentially calcium, strontium, and barium. Anything that is a salt, so it can't start with hydrogen, it can't end with hydroxide, but it must be marked with AQ. And then there are some also very limited molecular compounds, but that's more of an upper level topic. So just a reminder of what your 7 strong acids are. Very simple list. You've got hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric acids. Now these you should definitely memorize, because when you meet a new acid, if it isn't one of these 7 strong acids, it's going to automatically make it a weak acid. So now let's get right into the problems, right into the nitty-gritty, so to speak. Let's take a look at the dissociation equation for nitric acid. Now all acids need to react with water when they're becoming actual aqueous, once they're starting to dissociate. If we would just rip apart nitric acid into its 2 ions, we would have H1 plus and NO3 minus. Now the nitrate, the NO3 minus, is fairly stable on its own inside of a solution, but H1 plus is quite literally just a single proton. Just a single proton running around in a solution is not a recipe for stability. So instead, what it chooses to do is to kind of hitch a ride on top of water, making this kind of a complex ion hydronium, H3O1+. So anytime that you're writing a dissociation equation for any acid, water does need to be part of the reactant, and one of the products will always be hydronium, and then your anion. So here's our first cute little calculation. We have to calculate the pH of a 0.05 molar nitric acid solution. So again, the first step is always going to be to write out the dissociation equation, and that's just to try and look for any cases where we might have anything other than a 1-to-1 molar ratio between our acid and our hydronium ion. Now you should remember the majority of your pH equations from first year chemistry, but we will review those in a moment just to make sure that you have those down. So the first assumption that we need to make is that because this is a strong acid, it's going to dissociate to 100%. Therefore, if the concentration of the nitric acid is 0.05 molar, that means that the concentration of the products, since they have a 1-to-1 molar ratio, will be the same. So I can assume that my concentration of hydronium is 0.050 molar, as is my nitrate. Now my nitrate, not necessarily as important as that hydronium, because that hydronium is what's going to really force the change in the pH of the system. So if I would like to calculate the pH, all I have to do is to take the negative log of that concentration, and I find out that my pH is at 1.30. Here's a second example, and this one I find kind of important as well. Now with strong bases, when you're writing the hydrolysis or the dissociation equation for a strong base, you do not need to have water as a chemical reactant. Both the anion and the cation here are going to be stable in water. They don't need to react with water to try and gain any sort of stability. So our question here is calculate the concentration of ions and also the pH of a 0.02 molar barium hydroxide solution. So again, the first step would be to write out our balanced chemical equation, and notice that with this problem, there is a 1-to-2 molar ratio between my barium hydroxide and my hydroxide ion. And I'm really after the concentration of that hydroxide ion, as that's what's going to change the pH of the solution. So I start some calculations. Again, the big assumption that we need to make is that because it is a strong base, barium hydroxide being a strong base, that it will dissociate to 100%. So all of that 0.02 molar barium hydroxide will dissociate. And we can use multiple ratios to figure out the concentrations of my two ions. Now, the barium is easy. It will be the same since it's a 1-to-1 molar ratio. It will also be 0.02 molar. But notice the math here on the hydroxide. I did try and supply you with the multiple ratio. You can take the original concentration of that barium hydroxide and apply the 2-to-1 molar ratio between it and hydroxide to get the final concentration of 0.040 molar. All that's left now is to go ahead and start to calculate for the pH. Now, if I want the pH, I do need the concentration of hydronium ion, so there is a subsolving step beforehand. I can use the additional equation, hydroxide ion times hydronium ion equals 1 times 10 to the negative 14th. And do remember that that 1 times 10 to the negative 14th has an unlimited number of significant figures. So however many significant figures you plug into the problem is how many sig figs you can keep at the end. Hydronium ion concentration therefore comes out to be about 2.5 times 10 to the negative 13th. And if I take the negative log of it, I find that my pH is about 12.6. Now, one thing to remember is that water is kind of an interesting creature. Because it's really made from a hydrogen and a hydroxide ion, so to speak, it can really both be classified as both an acid and a base. So water actually contains the unique property of being able to react with itself. One water molecule will act as an acid, and one water molecule will act as a base. So just water sitting together in a cup will actually both have hydronium ion and hydroxide ion present in equal quantities inside of that container. Kind of interesting. Now, this is a very temporary state of being, so we can actually write an equilibrium expression with these ions in mind, and also we can develop an equilibrium expression. So we call this Kc, of course, because we're going to use concentration data. But notice that water, H2O, doesn't appear anywhere inside of it. And that's because the activity of any pure liquid equals 1. So really, it's really just hydronium ion times hydroxide ion. Now, of course, this is temperature dependent, like all Kc expressions. So generally speaking, the one that we're going to be worried about is at 25 degrees Celsius, or standard conditions. In this case, because this is again a constant, we're going to call this Kw because this is the equilibrium constant with respect to water, where hydronium ion times hydroxide ion equals 1 times 10 to the negative 14th. Now, although we call that a constant, for us, we know that at any given temperature that constant could actually shift. And there are tables and tables and tables of these published values out there, and they're very easy to find. So let's use this newfound equation for a new problem. Let's take a look at calculating the concentration of both hydronium ion and hydroxide ion in a 0.05 molar hydrochloric acid solution. As always, I do like to start with the dissociation equation. Again, because this is an acid, water does need to be part of the reactants in order to form hydronium and chloride ion. Notice also here my arrow choice. Because this is a strong acid, I'm using a single arrow. It does not create an equilibrium type expression. Because it dissociates to 100%, the original concentration of the hydrochloric acid will also therefore determine the hydronium ion and the chloride ion concentration. So great, we have our hydronium ion concentration, but we still need hydroxide. So remember that hydronium ion times hydroxide ion does equal 1 times 10 to the negative 14th. So we're just going to go ahead and plug and chug, and then we can find out that our hydroxide ion concentration is equal to 2.0 times 10 to the negative 13th. So here's a big question. We know that we're getting some hydronium ion from the autoionization of water. Why aren't we adding in that concentration when I go to calculate things like pH or the final concentration of hydronium ion when I'm just adding in 0.05 molar HCl? And the question actually comes down to sig figs. So from the autoionization of water, we could be expecting about a 1 times 10 to the negative 7th concentration of hydronium ion, just from the autoionization of water. But from the dissociation of the HCl, I'm going to have 0.05 molar. That, according to significant figures, is basically no contest. So it's not even worth our time to try and add in the concentration of hydronium ion from autoionization. It's pushed so far to the one side that we just shouldn't even worry about it. I think at this point it might be a good idea just to refresh your memory about some of the more important equations that we're going to see with pH. You might want to pause the screen and jot these down inside of your notes because they will be useful later on. One last point, which I think is actually kind of neat. Using this Kw expression, hydronium times hydroxide equals 1 times 10 to the negative 14th, there's actually a pretty interesting mathematical relationship that you can kind of see. So anyway, here let's do some math. Let's just take the log of both sides. So you can see I applied the log rule when I had hydronium times hydroxide. If I took the log of that, I'm going to separate those out and just basically add those two logs together. And now, just for fun, I'd like to take both sides times -1. So now it's going to be the negative log of hydronium minus the log of hydroxide equals the negative log of 1 times 10 to the negative 14th. And let's start to simplify this equation out a little bit. I know that the negative log of hydronium is pH, the negative log of hydroxide is POH, and the negative log of 1 times 10 to the negative 14th, well, that's 14. So just by doing a little creative math, we can actually generate a second very important equation, and that's that pH plus POH does equal 14. That can drastically speed up a number of calculations for us. And finally, just to summarize, there are essentially 6 extremely important pH equations. Remember that all of these are interchangeable. So once you start solving for one variable, it's very easy to solve for the remainder. It's just a matter of plugging and chugging.